Welcome to Math Zone African Motives. In this tutorial, we're diving into a powerful application of differentiation. Related rates. Today, our goal is to understand what related rates are and how to solve problems that involve them. Specifically, by the end of this video, you will be able to, first, identify the changing quantities and their rates of change in a word problem. Second, you'll learn to find the formula or relationship that connects all these quantities. And third, and most importantly, you'll be able to use the chain rule to differentiate the formula with respect to time to find the unknown rate. Let's begin. Before we tackle the main problem, let's build our foundation. What exactly are rates of change? We use differentiation to determine how quickly one variable is changing compared to another. For example, if we have a function y of x, the derivative x tells us the rate at which y changes for every unit change in x. But in real-world scenarios, things often change with time. If v is a function of time t, then dv dt tells us the rate of change of the volume with respect to time. Related rates problems involve two or more variables that are all changing with time and are related by some equation. If we know the rates of change of some variables and the value of others at a specific instant, we can find the unknown rate. Let's use a classic example, a spherical balloon being inflated. As air is pumped in, the volume V changes. Since the volume changes, the radius r and the surface area A must also change. All three, V, r, and A, are functions of time. The rate of change of volume with respect to time is dv dt. The rate of change of radius is dressage dt, and the rate of change of area is dE dt. Now, the first step is always to find the equation that relates the variables. For a sphere, the volume phi is given by the formula. V equals 4/3 PR cubed. Since both V and R are functions of time, we need to differentiate this entire equation with respect to t. We use the chain rule here. The derivative of V with respect to t, or dv dt, is equal to the derivative of 4/3 pi r cubed with respect to r times dt. This is the chain rule in action. The derivative of 4/3 pi r cubed with respect to r is 4/3 pi times 3r squared, which simplifies to 4pi r squared. So, our final equation is dv dt equals 4pi r squared dt. This equation connects the rate of change of volume and the rate of change of the radius. Because they are linked by this derivative equation, we call them related rates. Solving a related rates problem can seem challenging, but there's a systematic approach you can follow every time. Here are 5 essential steps. First, always draw a clear and simple sketch if the problem involves geometric shapes. Second, read the question carefully and write down all the rates and quantities you are given. Don't forget their units. Third, and this is crucial, find an equation that relates all the variables in the problem. This is the heart of the setup. Sometimes it's a standard formula. Other times you might need to use geometry like similar triangles or the Pythagorean theorem. Fourth, differentiate both sides of this relationship with respect to time, t. This step will introduce the rates of change. And fifth, substitute the values you know at the specific moment in time the question asks about, and then solve for the unknown rate. Before we dive into the main example, let's do a quick revision to make sure we're comfortable with differentiation with respect to different variables. We need to differentiate the function y equals x squared plus 2. First, with respect to x. Here, y is the dependent variable, and x is the independent variable. The derivative x is simply 2x. Notice that the derivative of the constant 2 is 0. Next, let's differentiate with respect to y. This is a bit different. We differentiate each term with respect to y. The derivative of y with respect to y is 1. The derivative of x squared with respect to y is found using the chain rule. We differentiate x squared with respect to x, which is 2x, and then multiply by dx di. So we get 1 equals 2x times dx di. Finally, with respect to time t, this is the case we'll use for related rates. Again, we differentiate each term with respect to t using the chain rule. The derivative of y is dt. The derivative of x squared is 2x times dx or dt. The constant 2 still differentiates to 0. So we have di/dt equals 2x dx dt. See how the chain rule is crucial when the variable we're differentiating with respect to is different from the variables in the equation? Now let's tackle our main problem. Example 333. Let's read the full question first. During an experiment, a steel ball soaked with oil rolls down an incline and collects sulfur particles at a rate of 250 cubic millimeters per second. The steel ball has a diameter of 50 millimeters. The question asks, how fast is the thickness of the layer of sulfur increasing when it is 10 millimeters thick? This is a related rates problem. Let's follow our 5 steps. First, step 1, a sketch. The diagram shows the original steel ball, which is a sphere, with a radius of 25 millimeters, since the diameter is 50. It's collecting a layer of sulfur, which has a thickness we'll call x. The total radius of the ball plus the sulfur is therefore 25 plus x. Second, let's list our variables and rates. The sulfur is collecting at a rate of 250 cubic millimeters per second. This is the rate of change of the volume of the collected sulfur, which we'll call V. So dV dt equals positive 250. The question asks for, how fast is the thickness of the layer of sulfur increasing when it is 10 millimeters thick? This is asking for dx dt, the rate of change of the thickness, at the instant when the thickness x is equal to 10. So our objective is to find dx dt when x equals 10 millimeters. We're now on step 3, finding the relationship between our variables v and x. The sulfur forms a spherical shell. A straightforward way to think about it is that the total volume of the ball with the sulfur is just a larger sphere. The volume of this larger sphere is v, the volume we're interested in. The formula for the volume of a sphere is a crucial formula to remember. The volume phi equals 4/3 pi r cubed. In our case, the radius r is not just a simple variable. It's the total radius of the steel ball plus the sulfur layer. From our sketch, the total radius, r, is 25 millimeters plus the thickness x. Now we substitute this expression for r into our volume formula. So our volume 5 equals 4/3 pi times the quantity 25 plus x cubed. This is the explicit relationship between the total volume v and the thickness x. This is the equation we need to differentiate. Now for step 4, differentiating our relationship. We have the relationship v equals 4/3 pi times the quantity 25 plus x cubed. We need to find the rate at which the thickness is changing, dx dt, and we know the rate at which the volume is changing, dV dt. This means we must differentiate this equation with respect to time, t. We'll need the chain rule here. Let's think of 25 plus x as an inner function and the cubing operation as an outer function. Differentiating pi and 4/3 is simple as they are constants. The derivative of v with respect to t is dv dt. The derivative of the right-hand side is 4/3p times the derivative of 25 plus x cubed with respect to t. First, we differentiate the outer function. This means bringing the power 3 down and subtracting 1 from the exponent. So we get 4/3 pop times 3 times 25 plus x squared. But we're not done. We must multiply this by the derivative of the inner function d dt of 25 plus e with respect to time. The derivative of 25 is 0. The derivative of x with respect to t is dx dt, so we multiply by dx dt. Let's simplify our entire derivative. The 3 and the 1/3 cancel out, leaving us with 4p. So dv dt equals 4p times the quantity 25 plus x squared times dx dt. This is our differentiated equation, which relates the rate of change of volume to the rate of change of thickness. We're now on the final step, step 5, substitution and solving. We have our rate equation. dV dt equals 4 times 25 plus x squared times dx dt. Now we substitute the known values from our problem statement. The rate of change of volume, dV dt, is 250 cubic millimeters per second. We need to find the rate of change of thickness when the thickness x is 10 millimeters. Let's substitute these values into our equation. We get 250 equals 4p times 25 plus 10 squared times dx dt. Simplifying, 25 plus 10 is 35, and 35 squared is 1225. So 250 equals 4p times 1225 times dx dt. Multiplying 4 by 1225 gives us 4900, so the equation is 250 equals 4900p times dx dt. Now, to solve for our unknown rate, dx dt, we just need to rearrange the equation. We divide both sides by 4900p. This gives us dx dt equals 250 divided by 4900. Using a calculator, 250 divided by 4900p is approximately 0.0162. Since x is a length in millimeters and t is time in seconds, the units for dx dt are millimeters per second. So let's write our final answer clearly. The rate at which the thickness of the sulfur layer is increasing, at the instant it is 10 millimeters thick, is approximately 0.0192 millimeters per second. The problem included a solution, so let's quickly compare our work to it to verify. Looking at the provided solution, it followed the exact same steps. It derived the volume relationship, differentiated it with respect to t, and substituted the values to get dx dt equals 250 over 4900p, which is the same as 0.0162 millimeters per second. Excellent. Our answer matches the provided solution. Verified using the memo. Let's quickly recap what we've achieved. We have successfully applied our 3 objectives for this video. First, we identified all the changing variables and their rates. Second, we found the relationship that connects them. And third, we used the chain rule to differentiate that relationship and solve for our unknown rate. You now have a solid framework for approaching related rates problems. Thank you for watching this tutorial from MathZone African Motives. We hope you found this step-by-step guide helpful. If you did, please give this video a thumbs up and subscribe to our channel for more MathZone African Motives tutorials. We'll see you in the next one.